This is part 2 of wireless LANs, and in this part we will cover A, B, G and N. So first we have the whole list of amendments that have been done to 11, that goes from A through AI, and then we go through and just define PDUs. Now this is again 473, but I'm just trying to make sure that everybody is at the same level. We'll define PDUs. What does PDU mean? Which many of you already know. And then A, B, G, N, we go through one by one, B, A, G, N, and so on and so forth. And then in the middle we have to do 11E. E changes the contention method that we talked about slightly. So we talk about that, and then we go through N, and then so let's move on to that. Okay. So as I said that every standard in IEEE is first developed and then they keep changing it because the needs change or because new things have to be added. So 802.11 was done in 1997. In 1999 they came up with A and B. The difference was A was running at 5 gigahertz band and B was running at 2.5, was running at a lower speed. It was called higher speed. This was actually running, B was running at 11 megabits and A was running at 54 megabits. Even though it was running at 54 megabits, nobody wanted it. That's why B came out before in the market than A. All right. So B came out, and because it was 2.4 gigahertz, and the standards people realized that they really need to work on that. So the next standard which came out in that series was G. Actually, not the next in the series, but the next in the terms of speed was G, which was taking all of A and putting it into G at 2.4 gigahertz. The problem here was 5 gigahertz band, as we'll see in a minute. In the middle they did 11C, which is the bridge operation, which has been moved to 802.1D. Now, here is one more thing just you should know, having taken a course on networking, is that IEEE standards are numbered such that 802 is the boss of all. So everything that is in IEEE 802 applies to all the 802.star standards. Okay? Now 802.3 is Ethernet, and then down there are other technologies, but 802.1 and 2 apply to all of those 802 technologies as well. So 802.1 is a general standard which applies to Ethernet, applies to wireless, applies to WiMAX, applies to everything that IEEE 802 does. And so does IEEE 802.2. All right. Now 1 has many substandards like A, B, C, D, like this, lowercase. But whenever you put an uppercase letter, that means this is not an amendment, this is not a change, this is the base standard. So I have seen a lot of people writing and mixing the cases, and that bothers me because these guys are writing and they don't know what they're writing about. So after this class, you should at least be careful about the case of the amendment. This is capital D, means this standard still exists and it will exist forever. Okay, if it was a lowercase, it will be merged with the base standard at some point. Alright, so capital D is the basic bridge standard for all IEEE 802 protocols. And 1D, so 1D is the base bridging standard, and so this 11C was merged into that one. Okay, and actually this was a misnomer, because if they would have realized that this is general standard, they would have called it 1D little a or something like that. Okay, and then they would have merged with 11D. But only after development they realized that okay, this is not just 11, this is everybody needs it, so they put it in the general standard. All right, so having done that, little 11D is global harmonizations, basically, as it says, files of the other countries. Every country has a different specs, different requirements, so on and so forth, so you have to worry about them. E is what we are going to discuss. So anyway, everything that is underlined here is what we are going to discuss. What is not underlined, this is the beginning and the end of that particular standard here. We are just going to tell you one sentence about it. All right? If you need to know more about it, of course, you can go back and just do your search and IEEE search and you can find it. But those are not of importance for us to discuss in this course. So, global harmonization we will not discuss. We will discuss E in detail. Quality of service. F is Inter-Access Point Protocol. It was never finished. Now it's capital F, but never finished. So there is no year with it. G we will discuss, that is similarly 54 megabits in 2.4 gigahertz band, and this was successful. So G came out before A in the marketplace, believe it or not. G is 2003, A is 99. People just didn't want to move up in the frequency spectrum. And H is dynamic frequency selection and transmit power control for Europe. Again, we are not going to discuss that. I is an important standard. It's on security, and normally we should have discussed this here in this class. However, security itself is a big topic by itself, and I'm teaching security course, network security course, hopefully next semester or whatever. So I'm just going to postpone it to there, okay? Because you need lots of background on security to understand that one. J is 4.9 gigahertz for Japan. K is how you measure the resources. M is maintenance. Basically, so what happens is every once in a while somebody will find out a bug in the standard and they will write to the IEEE and say, look, this is a problem, and then they will just maintenance. They will issue a maintenance record saying, okay, this has been corrected. So this is a maintenance. N, enhancement for higher throughput. So we'll discuss that one, 100 plus megabits. P is for roadside vehicles. Your cars will have probably pretty soon, maybe even next year, connection, so you can talk to the next car in front of you and give them all the help that they need. So you will have one more weapon in your pocket. That is coming up. Fast roaming is 11R. S is mesh network. All right, we will discuss that one. And then all of these were incorporated into 11, and that is called 802.11 2012. All right, so you won't find any of these now anywhere. If you go and look for 11N standard or 11A standard, they're all gone, removed from the IEEE library, because they're all merged into this big standard here, 2012. So you will find many 11s, like you will find 11-1997, then 2012. I'm sure there is one more in between, but I didn't write it. But anyway, 2012 is the latest. That has everything up to that point. Capital T, performance matrix. Now this will not be merged, as you know, from the case business. This is uppercase. U is the interworking with external networks. So if you want Wi-Fi to work with cellular nodes, how does this should work? That is specified in this standard. U. V, management. W, management. Protected management. Basically, up until this point, what they had done the security through I. Remember, the previous I standard is security standard 2004. However, it didn't protect association and disassociation, management frames. So if you want to connect to somebody, you could say it in clear, I want to connect to you. Right? If you want to disconnect, you say, I want to disconnect. But once you connected, then they will say, okay, what is your name, what is your address, what is your password, what is your blah, 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 and you will have a secure connection from that point on. Well, the problem with that approach is that anybody could say, oh, Rajan wants to disconnect with you, or I am Rajan, I want to disconnect with you. So anybody could disconnect you. They didn't realize this. These are all security experts working on security, but they didn't realize it, so this was fixed by this one. Protected management frames, W. Y is some new band which appeared 2.6 to 3.7. Then Z is direct data link setup with power save. So how do you talk directly to some station and still save power? Video transport, now AC is very high throughput, we will discuss that. AD is even very high throughput, we will discuss that. AE is QoS management. Anyway, so this is, as you can see, is 2012 already, basically this is where we are right now. Then there are standards which are still in the works. They don't have any year with them because they are still being done. So AF is white spaces, expected in March 2014, and we will discuss that. AH is sub 1 gigahertz, and we will discuss that. And this is important. There are many different frequencies here which I have written down just for completeness, but it is sub 1, below 1 gigahertz. Then Rev M, this is maintenance again, which is going to appear in March 2015. And AI is the fast initial link setup, expected in November 2015. So it's still almost 2 years away. Okay? So now you know one line for all of the amendments. All right? And we know which one we are going to discuss in this course. And let's just see how long will it take. Oh, sorry, there are 3 more. AJ is China millimeter wave, expected in 2016. AQ is pre-association discovery. Basically, before you associate, you have to discover and who is you have to discover not here in this room, but who is in the next room. Because if you are going from here to the next room, you really want to associate before you get there. So that is AQ. AK is the transient link within bridge networks. So sometimes you just want to go from here to there, but there is a link in the middle. Okay, you want to connect to the repeater. So they want to standardize that. All right, so that's the end. Okay? All right. So having done 11 standards, now let's go back to base 1. Okay, this is like defining packets. So the packet word is a very general word. This is not used by the standard bodies. Standard bodies like to use standard words like this, PDU, and actually the word PDU was invented when we were doing OSI, ISO OSI. How many people remember what does OSI stand for? Yeah.
Open System Interconnection.
Right. It's Open System Interconnect done by the ISO, which is just the opposite. Now, what does ISO stand for? Anybody know? Yeah. International Standards Organization, right? So ISO OSI model. And so, because there are so many layers, each layer has packet. So how do you distinguish layer 4 from layer 3 packet and layer 5 packets and so on and so forth? So you could call it layer 4 packet. That's what we do all the time. But really, there is a name for it called layer 4 PDU and layer 4 SDU, whatever. Okay, so I'm going to first describe, so for each layer, there is something called protocol data unit, PDU. So protocol data unit is the one that is used in the layer. So the layer 3, when it talks to the next layer 3, that they use layer 3 PDU. Layer 3, okay, is network layer, and therefore we will call it NPDU. Layer 2 is MAC layer, therefore we will call MPDU. Layer 1 is PHY layer, therefore we will call PPDU. All right. So for each layer, there is a PDU which goes horizontally, which is the thing that they talk to their peer on the other end. But what goes vertically is different. What goes vertically is called service data unit. So the MAC layer, whatever it gets, it calls it MSDU, MAC service data unit. Okay? So this is what happens. Whatever you get from somebody else, from the higher layer, that becomes your data. You don't touch it. Right? And you put some header and trailer on it, and that becomes your PDU. Right? So the PDU is SDU plus header and trailer in many cases. All right. So SDU is what comes in, and PDU is what goes out. Generally, the PDU doesn't go to the next neighbor right away. It goes to the next layer below, and therefore it becomes the SDU for that layer. Right? So MPDU becomes PSDU, and PPDU becomes, whatever it is, right? Next layer. So this is how the PDUs and SDUs flow. Now, what we have done here is actually the ISO had layer 2 called data link layer, but really afterwards when IEEE went in, they realized that really a data link has to be broken into 2 sub-layers. One is called logical link and one is called MAC. Okay? So you might even have a logical link SDU and logical link PDU. We are not going to worry about that because we don't use that much, but MAC we use quite a bit. Similarly, even though ISO had only one physical layer, people realized there are only 2 layers. One is physical layer convergence procedure, PLCP, and second is PMD. Basically, even in the physical layer, they have to do some bit work, let me put it this way. So you get 5 bits and you have to make it 7 bits and do something like that. That is all PLCP. Once you get the bits and you have to do modulation, that is PMD. There is no bit stuff in PMD. PMD is more waves and things like that. Okay? Analog stuff. So physical layer is broken into 2 parts. One part is the PLCP and the other is PMD. And PLCP does have a frame, does have a bits, it does have the header and things like that. So we will have PPDU. Okay? Everyone understand now PDU and SDUs, and we are going to use it quite often from now on. Okay, so PLCP PPDUs. PPLCP PDUs, which is PPDU. So PMD includes scrambling, randomization, coding, etc., etc. So it's not pure waves, but mostly, the base number remains the same. Then PLCP actually adds a header. To whatever MAC gives it, it adds this header. First of all, it adds a preamble, and then it adds a header. The preamble is a well-known pattern, and this pattern is generally selected so that there is maximum transition, so the receiver can figure out how long is the bit. Okay? So here is 01010101. This is just an example, by the way, because it depends upon what coding we are using. So 01 is 80 times 80 bits of synchronization. Then there is, this could be totally wrong, 18 bits. It could be 16 bit, but I'll have to double check that one. 16 bit of sync frame SFD. Now this is an example again, because every PLCP, and there are many of them basically depending upon what you are using for PMD, these things are different. So for example, just to say 11A will have a different SFD and things like that, and 11N will have different. They will have something in common so that you can figure out that this is A and 11, A and N, but after that they will be different. So the sizes are different in different kinds of standards anyway. Then there is length in bytes, 12 bits, signaling, data rate, 4 bits, and the head error check. So this is a CRC, 16-bit CRC, protecting what? It is protecting only these two 16 bits. So we have a 16-bit CRC and 16 bits of information. Alright? The reason it is such a strong CRC we need is because if you are wrong by the signaling data rate, the whole frame will be garbled. If you think it is 54 megabit and it is really 108 megabit, you won't get a single bit. So this is well protected by HEC. SFD is fixed. Start of frame delimiter is a fixed value that you look for, and as soon as you get that, you know that now we have to start looking for the header. Alright, this is a fixed pattern, and I have put a pattern here which is an example for some particular standard. And sync is, as I said, is a 0-1 pattern or 0, whatever pattern which gives you the maximum transition. Alright, so PLCP header. So now you know this is a PLCP PDU. Alright, What I have shown on the top is how the bits flow. So you want to send 0, 0, 0. First thing you have to do is scramble it. Why scramble it? Because most of the time people are sending 0, 0, 0, 0. If you keep sending 0, 0, 0, 0, and if the coding means 0, 0 means 0 volt, you will be in trouble because the other side will not know whether your wire has broken or you're really sending 0 volt. Right? So you want to send 1 at some point. And so the more changes there are in the signal that you're sending, the better it is for the other side to decode it. And therefore they randomize the signal before they send it. So even though you're sending fixed zeros, what comes out is a random number. The other side does exactly the opposite. Whatever random number they get, they run it through this scrambler and they get your zeros. Alright, scramble it. And then you then basically convert that into blocks. So this is a 4-bit block, and then 4-bit we have converted that to 6 bits. This is FEC, forward error correction. And then we just don't send the bits as they are, we intermingle them. What we do is, the problem is that when you have an error, you can detect 1 or 2-bit errors, but you cannot detect 10-bit errors. So what you do, you take 6 bits from here, 6 bits from there, 6 bits from there, and then you send them together. If they get all mingled up, then at least you have 1-bit error here, 1-bit error here, 1-bit error there. So that is interleaving. Interleaving means you take different blocks and put them next to each other. Okay, so that the errors will become dispersed. Make sense? Alright, so that is interleaving. So now we have taken this 0, 1, 0, 1, 1, 0, 1, 1, and then this one is the next one, maybe some other block, and then maybe another block, and then we have combined them. So we take 0, 0, 1, 0, 1, 1, blah, blah, blah. So we take 1 black, 1 red. And this is the stream we are going to send. Once we get that, now we make symbols out of this. So these are bit patterns. So let's say we do 2 bits symbol. We are going to do QAM, QAM, 4 QAM, or QPSK. So we need 2 bits at a time. 2 bits is a symbol. Right? So we just make it 0, 0, 1, 0, 1, 1, 0, 1, 1, 1, 0. So these are the 1, 2, 3, 4, 5, 6 symbols here. Okay? And then we do the modulation and out in the air. Alright, any question about any of these blocks? What? Why don't you?
Why do the interleaves?
Interleaving. Why does the interleaving happen? So anybody understands why interleaving happens? Anybody? Yeah, why?
To spread the errors out.
Yes, the thing is if you don't interleave, let's say you get the error here now, right? These 2 bits get into error, 0 and 1. With interleaving, 1 bit error will be here in the black one and 1 bit error will be here in the red one. Right? And you can correct 1 bit error in the red one because it is protected by 2 bits. Coming here. See what I mean? But you could not correct 2-bit errors in any block. You can correct 1-bit error. And so we want to make the errors dispersed. Now, one more, before you, his question, go ahead.
So is the 001100 also valid, also just random number?
This one is?
The red ones. Is that also data?
Oh, this is data. Oh, sorry. Okay, so this is basically you might get 5 blocks and you just take the second one and put it here, third one and put it here. Yeah. So interleaving takes the next 5 symbols or 5 whatever blocks to be sent and then puts them in, mingles them. So this is all pure data. Yeah.
How are you able to correct this data if it has an error?
Oh, okay. So this is actually coding. Again, let me just explain briefly. You all know parity. 1-bit parity can detect the errors. You understand that part, right? If you take, you just put even parity or odd parity, when you send it, let's say everything is odd parity. So there is even odd number of ones. When you get, and if you get even number of ones, you know that there is an error. But you cannot correct it. You don't know which bit is wrong. If you put more parities, suppose you put 2 bits, then you can figure it out that which 1 bit is wrong. Okay, that's why I have shown here 2 bits. So it is error correcting code.
You are doing this only because you want 2 bits per symbol.
Here? I'm sorry, what was the question?
You are doing this only because you are using 2 bits per symbol.
Okay, the question is, I am doing this because I have using 2 bits per symbol? No. I could use 3 bits per symbol, or I could use 1 bit per symbol. I still need to do all of this. The thing is, errors could be multiple symbols too. Even if I am doing 1 bit per symbol, I could have 5 symbols in error. Burst error, burst error can affect many symbols. But with this interleaving, the 5 errors probably will appear in 5 different places. Yeah, next question.
Do you only interleave 2 blocks at a time?
Oh, no. I couldn't draw, here enough vertically. So you interleave many blocks. The question is whether you interleave just 2 blocks. No, you could have 3, 4, 5 blocks.
So how do you know which bits belong to which block?
Oh, because this is all agreed. You know exactly what I'm sending you. Okay? All right. So now we are ready to talk about 11B. 11B is pure direct sequence spread spectrum. So you take 0 and have an 11-bit sequence, and 1 have an 11-bit sequence. Okay. The reason this picture you have seen before. The reason I put it here again is because I forgot to define a word called chips. So these bits can be called code bits, but they are more frequently called chips. These are data bits, and generally we don't call data bits, we just call them bits. So these are bits, these are chips. Okay? And so in 11, standard 11, they were just having 1 bit per symbol and 11 chips per symbol, and using DQPSK, they got 2 megabits using 22 megahertz. So they didn't use 20 megahertz like we said before, they used 22 megahertz. Now that actually answers the question that somebody had asked in the class as to why the channels were made 5 megahertz and why we are just using 1, 11 and 6, and why don't we just use 1, 2, 3, 4, 5, 6, 7. So the answer is that the channelization is done standard, maybe FCC or somebody does it and so says here are the channels 1, 2, 3, 4, 5, 6, 7, 8 to 20, and the usage is done by the standard bodies, and they can decide how much we want to use. So as you will see in this series today, some standards use 4 channels, some standards use 5 channels, and they call their 1 channel. Alright, so the channels that are used by the standards are different than the channels assigned by FCC. FCC doesn't say that you cannot use more than 1 channel. And after all, it is free channel. So you could use, if you suppose FCC says, well, you can use only 1, then people will say, well, I have 2 computers. They are each using 1. Or my computer has 2 parts. It is using 1. So you cannot count how many channels, how many users there are. So number of channels is different. So in this case, in the original standard, they were using 22 megahertz, and using 11 chips, they got 2 megabits. 11B fixed very simply by changing the coding so that they didn't use 11, they used only 8, and they just didn't use 1 bit, they actually used 8 bits and 4 bits. So they took 4 bit, for example, and then 16 combinations. They still had 8 chips. So for each of the 16 combinations, there were 8 chips. So like that. Similarly, for 8 bits, they had 64. Sorry, not 16. So 8 chips means you'll have 64 codes. So you will have 64 codes for 64 symbols here and so on and so forth. And so they got 11 megabits using 22 megahertz. And this kind of thing is called complementary code keying, CCK. Now CCK is much more complex. Again, let me tell you, if you go to Wikipedia and read about CCK, it goes into imaginary numbers and complex things and so on and so forth. Again, that is important for people who do wireless communication. If you were ever to do a product on this, I would recommend that you understand all that mathematics. Okay? But most of you, being computer scientists, probably are going to write code for it rather than do any hardware. And therefore, I'm just concentrating on the code part of it right now. So CCK is take multiple symbols with appropriate multi-bit symbols. So you don't have to have just one bit. You are going to have, you take 4 bits, 8 bits. And then you convert that into chips. Okay? And that way you minimize the errors, and then you can also distinguish from other people and so on and so forth. Everybody has a different set of codes. So that is CCK, and CCK is changed the speed by a factor of 5.5. That's all. There is nothing much, and that's why it came out very early. It was right away adopted because people already had the products. All they had to do was this CCK stuff, which is either little change in hardware or little change in software, whatever. So that was 11B. By the way, this book, 11 Wireless LAN Fundamental, which is Safari book 2003, I found it very easy to read. So I have 2 books referred in this lecture today, and I would really encourage you to read those 2 books. Okay? They are very straightforward to read. This is one of them. The second one is even easier, and I like even that one even more. So anyway, so we'll come back to that. Yeah.
Shouldn't that be 22 megabits per second using 22?
Yeah, so that's a very good question. The question is, if you're going to do 8 bits per chips and DQ DSP, why don't you get 22 megabits per second? If you do calculation, which he did, and I did it too, you really get twice as much, right? But 50% is lost somewhere in this CCK stuff, and it's not easy to explain and it's not easy to understand. So you are right though. I mean, I have the same question, is that if you have 8 bits, you get, basically, 1 bit per chip. And DQSP will gives you 2 bits, 22 megahertz, you might get 44, something, right? But there is a little bit more math here where in the middle somewhere they lose that factor. Okay, because it is a little bit more complicated. What they do is they take the 8 bits and then they use the 6 bits to find the code and the 2 bits to do something else. So the coding is a little more complex, and therefore there is some detail missing here which somehow reduces it to 11 megabits. Thank you for that. So you're listening, at least I know, and thinking. Okay, anybody else? All right. So we move to 11A. 11A's new thing was OFDM. Remember this 98-99 time frame, OFDM had just come in. And OFDM, so they did 64 carriers in 20 megahertz. So they took, not 22 now. See, they changed. B uses 22, A uses 20. And they took 64 carriers, and they don't use these 6 at the end because they might be affected by the other people. And so they are used as guards, and then 4 are used as pilots. So you have 48 for data. All right. Now, if you really do the math again here, 64 in 20 megahertz, so 48 gives you a little bit more than 12 megahertz. 64, 20 divided by 64 times 48 is 3/4 of 20, 15 megahertz is something I get, but 12 is what you really get at the end. So where is those 3 megahertz go is another little detail that I couldn't figure it out, but basically you get 12 megahertz, and with 12 now you can explain everything else. So with 12, if you use BPSK, you get 1 bit per hertz, so you get 12 megabits, and you do half FEC. This is called code rate is half. Forward error correction rate is half, which means that for every bit you send 2 bits. Alright? So when you, on the air, when you get 2 bits, only 1 bit is data, and therefore your rate is 6 megabits. If you do same BPSK, you get 12 megabits, but you can change FEC to 3/4. For every 3 bit you send 4 bits. Then on the air you get 9 megabits per second. And so on and so forth. And now you can do all the calculations, they all perfectly work out. Okay? All the way to 54 megabits. That's how we get 54 megabits on the air. Obviously the user doesn't get 54 megabit. It is 54 megabit on the air. A lot of it is lost in the, in RTS, CTS, spaces, waiting, overhead, headers. So by the time you get maybe 20 megabits. But this is the rate that they advertise in the papers. When you buy, they say it is 54 megabit. If you get 50% of that, you are lucky. And obviously they cannot put 55 megabit because that would be incorrect and they will be sued. So 54 megabit is what they get away with. Okay? And obviously you won't be able to get coding of 3/4 and 8 bits QAM go through that one, because that really requires a very clean environment to get that high coding rate and with that little protection. Right, so 54 is again something that is possible theoretically, but in practice you get much less. The main problem with 11A is the band, 5.4 gigahertz band. Now everything becomes expensive when nobody else uses it, but it becomes cheap if everybody else uses it. So that's the problem with 5.8 gigahertz. In 99, nobody else used it. So you had to really order it from special factories, pay a high price, and nobody will buy it from you then. Now it is just everyday affair. Everybody makes it and everybody buys it. So 5.8 was not used at the time. Okay, so now we are back to G. Okay. So G came out. So as soon as A came out, people realized that, oh, we made a mistake. We had the good technology but the wrong band. So they said, let's fix the band. And they fixed the band by just going to 2.4 and using everything else just like A. And so that one has one more advantage, that because you're in the right band, if your thing didn't work out, OFDM didn't work out, you could just do CCK. So with A, you just had A. With G, you had BG. Everything that came out with G was BG. Had a B as well as a G, because the band was right. Okay. Now, before we come to N, which is quite some time, people are happy with BG. So we have to fix the quality of service. 11E. And 11E is basically enhanced quality of service. So they did five different things. 1, 2, 3, 4, 5. First of all, they changed the coordination function. So remember, you had DCF, PCF. PCF was point coordination function. DCF was distributed coordination function. You had contention free period and contention period. Right? All of that was changed with 11E. So now we have, instead of PCF, we have HCF, hybrid coordination function. Instead of DCF, we have EDCF, enhanced DCF. And not only that, with each beacon, you don't have to have PCF and DCF just once. You could have as many HCF, DCF as you wanted. Alright, so what difference does it make? It doesn't really make much difference yet until you understand what is HCF and EDCF, right? So that we will explain in the next slide. Direct link. Second thing they realized was that you really don't need to go to the access point for everything. So prior to this, everybody, if I want to talk to you, I talk to the access point sends the frames to you. So 2 hops for 1 hop. That was a waste. So they fixed that one by direct link. So now I could send an RTS to you and not to the access point. Okay? That is direct link. Frame bursting. And the second thing was that every time I did the RTS, I had to send one frame and then I had to sit down and do RTS again. A lot of waste, particularly at these high speeds. At 2 megabits or 1 megabit, nobody cares. But at 554 megabits, we care that so much time is being wasted in just RTS, CTS stuff. So if you get once clearance, you might as well send 10 frames. They don't take that long at 54 megabits. All right, so frame bursting. And group acknowledgement. So basically, if you get 10 frames, you can say, I got all 10. Multiple priority levels. And the fourth thing is that now not everything is the same priority, so we allow multiple priority levels. And automatic power save delivery. And we want to save more power so we can let people sleep more, and when they wake up, they have to do less. Okay, so let's see all that in a detail in a minute. But these are the 5 things they did. However, this is all compatible. So if somebody doesn't have 11E, they can still work with the 11E stuff because 11E understands them. Yeah.
You mentioned in this scenario that the 2 machines can talk to one another. In general, the AP does the authentication, so will the machines be authenticating the messages between them?
Yeah. So basically what will happen is when you have to associate with the access point. When you associate with the access point, you get the keys and things like that. And the other station has associated with the access point and they get the keys. So once we have exchanged the keys, now we can talk. Right? And so that security stuff is all in the background. You cannot just come into a network and start talking to somebody. Okay? Because there are so many other parameters that have to be negotiated. So yes, you have to associate with the access point. Any other question? All right, so what is enhanced DCF? EDCF or EDCA as they call it, distributed coordination access. So basically they allow, instead of 1 queue, now you allow 4 queues. Each queue has its own minimum, CW min, CW max, and what we used to call diffs, now we call AIFS. We could have called it diffs, but they call it AIFS, arbitrated interframe spacing. Old diffs is now called AIFS. And then there is something new called TXOP, transmission opportunity. This is basically, instead of saying that I want to send 1 frame, you say, well, I want to send for 5 microseconds, or I want to send for 50 microseconds. So transmission opportunity. And so this is actually also limited. So this is actually the upper bound on that, is that if you are in this priority 1, maximum you can send is this much duration. If you are in priority 2, these are your parameters. Now BO is back off. So for each of these queues, there are so many parameters now. Have any of you ever set any of these parameters? None. And so that is the thing, is that most of the time whenever these things come in, they are basically, people are just don't have time to use them, and they don't use them, and so either they are default in your system, and your system might say, well, video, okay, all right, you have video, and I don't know how you tell them that this is video, because I have no way of telling my router that this is a video I'm watching. So they have to figure it out that I'm watching a video, right? Somehow if they figured out what they're watching a video, they will put into the right queue. Otherwise, everything goes to the same way. All right, but it is there. In case you care, then of course you can go into your router and look under as to how many queues it has and what are the values and how you submit it. But having said that, all we have done is now we have done 4 priorities with 4 different parameter values, and now you have to understand this, that if you are in a high priority, you cannot be hogging the line, so your transmission opportunity would be small. high priorities can do only small time. Lower priorities, because nobody else high priority wants it anyway, they can transmit for a long time. Right? Your backoff would be lower. So if there is a contention, your backoff CW min and CW max would be smaller than these others. Actually, right. In fact, I'm saying the same thing. CW min and CW max will be smaller, and so would be TX op, AIFS. All of these would be smaller, right? For higher priorities traffic. All right. So that brings us. So that is the EDCF. Any question about EDCF? You drew the picture for 1 priority. Now you can draw the picture for 4 priority, right? So it's just that everybody will have a different parameter value depending upon what priority they want to send. Now, frame bursting is similar. It is straightforward. Whenever you get the opportunity, you send many frames up to the TX op limit. So this is the limit. You can send 1 data frame, get the acknowledgement, 1 data frame, get the acknowledgement, 1 data frame, get the acknowledgement. You can do all that. All right. So the limit is not on the number of frames, the limit is on the time. And so voice, for example, will have high priority but small burst size. Video will have a lower priority but large burst size. Right. All right. Now, so here you can do acknowledgement of each frame, but as I said, you could also do a burst acknowledgement if the sending party agrees. Basically, you have to negotiate because the other station may not understand group acknowledgement, may not understand this and that. So for every feature, you have to negotiate with the other side. So if they understand block acknowledgement, then you could just send data, and then at the end, you could get the acknowledgement. Direct link is straightforward. No magic here. Is that you don't have to go through 2 hops. You can just go 1 hop. Automatic power save delivery. So now we didn't actually do the power save delivery very well last time. I'm going to do it now. Is that previously what we used to do was that access point, and basically what happens is when a station goes to sleep, it either tells the access point saying, it tells access point that I'm going to go to sleep now. And then it just goes to sleep. And whenever there is a frame to that access point, to that station, STA is the word for station, by the way. IEEE word. So whenever there is a frame for that station, access point will save it, will not transmit it. But it will put into the beacon that I have a frame for station number 13, 15, 27, and 23. All right? So everybody, when they wake up, they listen to the beacon, and if they see their name in the list, then they send a poll to the access point, say, can you give me my frame, please? That's a poll. And then the access point will send them 1 frame with a more bit set. If the more bit is set, that means I have more frames for you. So then we'll get that frame and say, okay, can you give me the second one? Okay, second one. More. Third one. More. No more. Done. All right, so that is how the previous savings worked. This was good because at least I could go to sleep. However, there is some extra work that doesn't need to be done is being done. First of all, why do I have to poll for every frame? Second of all, why do I have to poll for any frame? All right, can we save that time? And that is what E did. 11E has 2 unscheduled APSD and scheduled APSD. In scheduled APSD, you say, well, I wake up every day at 6 a.m. All right, I'm going to go to sleep. I will wake up at 6 a.m. Now, at 6 a.m., the access point doesn't wait for anything. At 6 a.m., it sends all the frames to you. All at once. All right, so we saved all of that overhead of polling and more and polling and more and polling and more because you wake up at a fixed time. And why do people wake up at a fixed time? Because they're watching video. Video comes at a fixed time. Every 30 milliseconds there is a frame. So you can go and sleep for 29 milliseconds and then you come back and you get your frame and you go back to sleep. Right? So if you have a periodic traffic, then you do scheduled APSD. Unscheduled APSD is like previous one, where you don't know when you will wake up. So you just wait for the beacon, and when the beacon, they listen to the beacon, they send a polling frame, and access point sends all the frames. So the main thing we saved here is more bit. We don't have to wait for the more part, we can just send it to you. Now you are awake, take here 15 frames. All right. So now you can see EDCA parameters. So we have background traffic, which is the lowest priority, best effort little bit higher, video little bit higher, voice the highest priority. Highest priority is CW min would be like this. Okay, this is 1/4. So this voice has CW min, which is almost 1/4 of the first one. CW max is 1/2 of the first one. AIFS, the time that you have to wait is smaller for these guys. These guys have to wait longer. If nobody else is using it, then the media will be idle and then these guys can use it. And the TX op limit, how long you can transmit depends upon how much speed you are running at. At 11 megabits, the limits are 6 milliseconds and 3 milliseconds. At 54 megabits, 3 milliseconds and 1 millisecond. Okay? So now you can see what the priority does. With priority, you have to wait less, but you have basically and you have to wait less, right? Yeah, half and 1/4 less sometimes. And with lower priority traffic, they have to wait longer. Okay. One question that came to my mind is, what does 0 mean? And I have to verify that. 0 means that you can just transmit one frame and be done with it. As opposed to 0 means no limit. All right, you transmit one frame. That is my interpretation right now. Okay. Is then, and then you see if no higher priority traffic comes back, you transmit the second frame. If nobody comes back, you do the third frame, and so on and so forth. Whereas these guys don't have to do that. All right, that brings us to 11N. 11N came in 2009, so you see there is a big gap between whatever we had 2003 and 9, 6 years. And by this time, the world was much better in terms of wireless knowledge. So things are much better. What is new here now by this time is MIMO. Multiple input, multiple output. Now MIMO requires two things. It requires the antennas, but it also requires the logic inside the station. And you don't have to have both. So you could have more antennas but not the logic, or you could have, so that's it basically. You will have as much logic as the antenna. Suppose you have 4 antennas, you could have 4 circuits inside, you could have 3 circuits or 2 circuits. You cannot have 5 circuits. That would be waste of time, right? So you have to specify 3 numbers, in and out, transmitting antennas, receiving antennas, colon, the number of chains, as we call them, radio chains that you have inside. and this is actually the minimum of the two sides. So if the transmitter has only two radio chains and the receiver has three, it doesn't help, because transmitter is going to send only two. So that is the minimum of the two, right? So n times m colon k, n transmitters, m receivers, and k streams, and this has to be less than the number of antennas. So we have these combinations: 2 by 2 colon 2, 2 by 3 colon 2, 3 by 2 colon 2, 4 by 4 and colon 4. Right? You cannot have 3 by 2 colon 3, because somebody who has two antennas will have two chains. Right? And you cannot get throughput more than the number of chains. So if you have 3 by 2 colon 2, your throughput will be 2 times. Actually, what will happen is, if you had only 2 by 2 by colon 2, your throughput will still be 2 times, but here your chances of getting 2 times is much higher, because the signal will be much cleaner. You will have much better knowledge of this so you do gain by antennas. Remember that diversity stuff. By having more antennas, your ability to remove noise would be much better. Okay, so you might be able to use FEC much better, and so on and so forth. So yeah, it's good to have more antennas, but your total throughput will still be, maximum would be 2 here, maximum would be 2 here, but the chances of getting 2 here is much higher. This is all probabilistic. Alright, so we know MIMO. Now diversity is basically saying that more antennas than the chains. So we allow you to have 3 antennas and 2 chains, and so on and so forth. And so that is diversity. Beam forming is focusing the beam in a direction, and actually more like, changing the direction. So if I'm talking to 2 people, I could be changing it here first, sending a frame there, and then sending a frame there, and then sending a frame here. So being able to move your beam is beam forming. MIMO power save is that if you have 4 antennas, why waste money when nobody is listening to you? Everybody has 1 antenna, so then you can turn off 3, and so that is MIMO power save. Okay, any question about any of these 4? More. Frame aggregation. So we talk about frame bursting, but 11N is later than E, right? So 11N people came up with frame aggregation, which means you take multiple frames and transmit inside a frame. Okay? This is opposite of frame fragment. I have a slide actually on this later on. Frame fragmentation means that if you have big frame going out, you just break into pieces, right? So frame aggregation is just the opposite. If you have little frames going out, you put them into one frame. Frame aggregation. Lower FEC overhead. Now they started allowing 5/6 instead of 3/4. 3/4 was maximum before. Now you can go 5/6. Reduced guard interval. So before every symbol, you just put some space so that they don't collide. And here, the standard was 800 nanosecond before. Now it is 400 nanosecond is allowed. Reduced interframe spacing. They just actually squeezed out every little bit and byte everywhere. And so CIFS was 2 microseconds before. 10 microseconds before. Now it is 2 microseconds allowed. Okay, it's a lot of time. Greenfield mode. Now what is greenfield? Greenfield means there is no installation before. So the thing is, when you have 11N and everybody else has B and G, you have to speak B and G and N. Right? Greenfield means there is no B and G. You started a new company, new building, new everything, everybody has N, you have N, you can do much better. So there is a greenfield mode. Dual band, it runs at both 2.4 and 5.8. 11N runs at both. So you can talk to A, you can talk to B, and therefore now you get A, B, G, N. Because N can talk to A and G. Space-time block code, this is a new kind of coding. Channel bonding, you can use two 20 megahertz channels. So instead of 20 megahertz, now use 40 megahertz. So that's 5 megahertz. Basically, you use 8 of them. Right? And more subcarriers. Now, if you use 8 of them, then you don't need to use guard as much. And so instead of 52.4 in 20, instead of 48 plus 4, they can now use 52 plus 4. So they started using a little bit more guard and less guard. And then with 40 megahertz, they use 108, which is even more than double. So 52 times 2 is 104. They use 4 more and less pilots. So all of this. So if you do all of this, then with 4 streams, 4 antennas, 4 logic chains, 5 by 6 FEC, highest FEC allowed, 40 megahertz, the highest bandwidth allowed, 400 nanosecond, which is the smallest thing you can do. The best you can do is 600 megabits.